Go ahead, take a breath, a nice deep one. You do that about 20,000 times a day, and you probably never, ever think about it. But that simple little act, it's one of the most complex and honestly elegant processes in the entire universe. So let's dive in and follow the incredible journey that every single one of your breaths takes, from the air all around us to the very core of your cells.
So, here's what we're going to cover. We'll start with the sheer miracle of just getting air where it needs to go. Then we'll track oxygen as it actually enters our body. We'll meet the amazing delivery service that carries it around. Then we'll see how doctors can even measure this stuff. And finally, we'll see how it all comes together in a literal life or death decision in surgery.
All right, first things first. The biggest challenge for any big, complex creature like us is really a logistics problem, right? How do you get oxygen from the air outside to literally trillions of cells that are buried deep, deep inside your body?
Well, this simple little diagram is basically our roadmap for this whole explainer. See, our respiratory system uses two main tricks. First, there's convection. Think of that as the highway system. It's the bulk movement of air into your lungs and blood pumping around your body. And then you've got diffusion. That's the local delivery, where the gases have to hop across these tiny barriers to get to their final destination. And the whole point of this incredible system is to do something called gas exchange. It's a two-way street, you know? It's not just about taking in the good stuff, the oxygen. It's just as much about getting rid of the waste, which is carbon dioxide. That exchange, right there, is the entire reason we breathe. Now, to make that exchange happen fast enough, your body needs a gigantic surface area. And the scale here is just mind-blowing. If you could actually unfold all the tiny little air sacs in your lungs, all of them, they would cover up to 100 square meters. That's about the size of a tennis court, all packed neatly inside your chest. Wild, right? Okay, so we've got this massive tennis court-sized area inside us. But how does the oxygen from the air around you actually get down into those tiny little sacs, the alveoli? Well, the answer is just simple physics.
Yeah, it really all comes down to this one basic rule. Just think of oxygen in the air as being under high pressure, and it's always looking to move to an area of lower pressure. And because the oxygen pressure inside your lungs is lower than it is in the outside world, oxygen doesn't need to be pulled in. It just falls in. It flows downhill, all on its own.
So the oxygen has arrived in the lungs. Now, how quickly can it hop into the bloodstream? Well, that's governed by something called Fick's law. This formula might look a little scary, I know, but it's basically just the recipe for super fast, super efficient gas exchange. And here's what that recipe calls for. For fast diffusion, you need a big pressure difference. Check. We've got that. You need a huge surface area. That's our tennis court. Check. And you need a really short distance for the gas to travel. The wall between the air in your lungs and the blood in your capillaries is unbelievably thin. And by the way, this is exactly why something like smoking is so bad for you. It thickens this barrier, directly slowing down this critical process. Our lungs are just perfectly engineered to nail every single part of this recipe. Okay, so the oxygen made the jump. It's officially in the blood. But how does it get from your lungs all the way down to, say, the muscle in your pinky toe? Just dissolving it in blood plasma won't cut it, not even close. We need a special delivery service. And that delivery service is called hemoglobin. This incredible protein is packed into our red blood cells, and it acts like a massive fleet of tiny little oxygen taxis. Each one can grab up to 4 molecules of oxygen in the lungs and then cruise through your bloodstream to drop them off wherever they're needed. This S-shaped curve is kind of the secret to hemoglobin's genius. So up in the lungs, where there's a ton of oxygen, the curve is really steep and then flat on top. What that means is hemoglobin gets super greedy. It just grabs and grabs and grabs oxygen until it's almost 100% full. It's like all the taxis are loaded up and ready to hit the road.
But here's the cool part. Hemoglobin isn't a dumb taxi. It doesn't just drop off its oxygen anywhere. It's smart. It looks for signals that it's in a busy neighborhood. You know, where the cells are working hard. And what are the signs of a hardworking muscle? Well, it gets warmer, it gets more acidic, and it's pumping out more carbon dioxide. As soon as hemoglobin senses those things, it knows, aha, this is the right stop, and it unloads its precious oxygen cargo right where it's needed the most.
So we've seen this amazing microscopic ballet of molecules and proteins. It's incredible. But how do we zoom out and actually check the performance of the whole system? How can doctors measure our lung function and understand the language of our breathing? It seems like a tricky question, doesn't it? I mean, how can you put a number on something as automatic and invisible as a breath? Well, it turns out we actually can, and with some amazing precision. This chart shows us exactly how. See that gentle little wave in the middle? That's your tidal volume. That's you right now, just breathing normally. And that huge mountain and valley? That's your vital capacity, the absolute biggest, deepest breath you can possibly take in and force out. By measuring these volumes, doctors get a really clear numerical picture of just how well your lungs are working. And here's why these numbers are just so powerful. Look at this comparison. With restrictive diseases, like lung scarring, everything just gets smaller. The total size of the lungs shrinks. But with obstructive diseases, like COPD or emphysema, something totally different happens. Air gets trapped inside, so the amount of air you can't push out actually gets way, way bigger. These patterns are like a fingerprint for diagnosing specific lung problems. Okay, now let's bring everything we've talked about together. We've covered physics, we've covered chemistry, we've covered measurement. Now let's see why it all matters in one of the most high-stakes scenarios in all of medicine, figuring out if a patient is strong enough to survive major lung surgery. You see, when a surgeon has to remove a piece of a lung, there's a cost, a permanent one. This chart makes it super clear. Removing a small wedge might only cause an 8% drop, but a pneumonectomy, that's removing an entire lung, causes a massive 35% permanent reduction in your ability to breathe. That is a huge, life-changing number. And this is where the numbers become a matter of life and death. This graph plots a patient's age against what their lung function is predicted to be after the surgery. And you can see it plain as day. The risk of death climbs like a rocket as a patient gets older and their lung function gets lower. Surgeons use this exact kind of data to have very real, very tough conversations with patients about their odds. And all of that data gets boiled down into a decision-making playbook that looks just like this. It starts with those basic tests we talked about, the ones that predict what your lung function will be after the operation. If the predicted numbers look good, say over 40% of normal, then it's a green light. If they're low, you do more tests. But if they fall below a certain critical point, the recommendation is crystal clear. Do not operate. The risk is simply too high. And if you want to know just how high those stakes are, just listen to this quote from the source material. A predicted lung function of less than 40% after surgery was tied to a 50% mortality rate. 50%. That's a coin flip. And that is why every single measurement, every single calculation is so absolutely critical. So we've gone from the simple physics of air pressure all the way to a deeply complex ethical choice. We've seen that every single breath we take depends on this incredible, intricate balance of engineering and chemistry. So I'll leave you with this question. Knowing everything that has to go right just for you to take one easy breath, how does that change the way you think about that razor-thin line that doctors and patients have to walk between medical risk and reward?